Hey guys, Mr. Betts here. So we've talked about what it means for a function to be discontinuous and kind of an informal definition of what it means to be continuous. We can kind of think of a continuous function as a function we can just draw on a coordinate plane without lifting our pencil up. And based on that informal definition, we could come up with why a function might be discontinuous. What I want to do is actually use these limits that we've been talking about to define continuity and then look at those discontinuities and talk about why we actually say they're discontinuous. So first of all, this is the formal definition of continuity. And basically what it says is that for a function to be continuous at a particular point, so this is for continuity at a point, for a function to be continuous at a point, the function has to be defined at that point. So this fits in with our informal definition of just drawing the function. To draw it, it's got to have a point there. But then also it includes the limit as x approaches that point. So that limit has to exist. And the third and final thing, this is kind of the most important thing, is that those two things are equal to each other. So as x is approaching the point, it's approaching the value that f of c takes on at that point. And really, this third condition here is sufficient to define continuity, because if this equation is true, that means the limit has to exist. That means the function has to exist for them to actually be equal to each other. So what I want to do is I want to take this definition and look at those examples of discontinuity that we talked about and talk about why, based on this definition, those are discontinuous. So three of the types of discontinuities that we talked about are removable, jump, and infinite vertical asymptotes. We also talked about oscillating discontinuities. That's not going to be as important. We won't see that happen very often. So I'm not too worried about that one. So first, let's look at a removable discontinuity. This picture right here shows us a removable discontinuity. So it's essentially looks like a continuous function with the exception of a hole right there. So let's talk about why this doesn't fit with our definition of continuity. And really, it fails on the very first one. So step number one, or condition number one, says f of c has to exist. Well, at this point, at x equals c, the function doesn't even exist here. Now, I could get around that. Let me redefine the function here and just say f of c is this point right here. That's still a removable discontinuity. So this one now is met. The second condition is also met because the limit exists. It's approaching the same value on the left side and the right side. But then when we get to step three, these are not equal to each other. So f of c is here, the limit is here. They're not equal to each other, so this is discontinuous. If we look at a jump discontinuity, so this would be if I'm drawing with my pencil and I get to a point here, I have to lift it up and go to another point to continue drawing. That would be a jump discontinuity. So in this particular example, the function does exist at the point. Even if this were an open hole and this didn't exist, we would run into trouble otherwise. Where we run into trouble here is this one. So in this particular example, the left-handed limit exists and the right-handed limit exists, but the limit at the point doesn't exist because those are approaching different values. So condition number two is not met. This is discontinuous. Last one I want to look at is an infinite discontinuity. And in this example, kind of like the first one, the first condition is not met, but we can make that be met just by defining it on the asymptote somewhere. So whether or not this one is met, we're going to run into trouble on number two. So number two says that the limit exists. In this case, the left-handed limit approaches negative infinity. The right-handed limit approaches positive infinity. And even if they were both approaching positive infinity, and we might even say then that this approaches positive infinity, even if f of c exists, it cannot equal infinity. So then we would run into trouble on the third one. Generally, we say if we have this vertical asymptote, the limit does not exist. We could be a little bit more precise. in describing what's going on with the function if we say that limit approaches infinity, but that limit doesn't exist. So condition 2 is not met, and this is not continuous.